Hello everyone, welcome to my talk. Today I'm going to talk about four-dimensional aspects of tight contact three manifolds, and everything I'm going to say is based on joint work with Matt Hedden at Michigan State University. Okay, let's get started. So I want to start out by just telling you, or maybe reminding you, what a Legendrian knot is. So first, let me tell you what a contact structure is. So a contact structure on a three manifold is a maximally non-integrable two-plane field. I call it XI. And if I look at the tangent bundle of my three manifold, it splits as a Whitney sum of the contact planes and the orthogonal complement. And we say that our contact structure is co-oriented if this this orthogonal line bundle is oriented. So for the duration of the talk, I'm just going to assume that all of my contact structures are co-oriented. I won't say that again, but that assumption is there for the remainder of the talk. And okay, so here's a picture of a contact structure on S3, and if I think about a knot inside of my three manifold, I call this knot Legendrian if its tangent bundle sits inside of the contact plane. So here's a picture of what I mean. Basically, I'm just saying that at every point, the knot that I've drawn is tangent to the contact plane. So it's tangent there. Maybe that's a little tangent vector. Over here, it's going that way. Over here, it looks like that, etc. So this is a Legendrian knot. And today I'm going to talk about really we're interested in studying surfaces who have boundary Legendrian knots. Okay, so there's two, when you're talking about Legendrian knot theory, there's two sort of classical invariants that come up. The first one is called the Thurston-Bennequin number. And here's a definition. It's the linking number between K and K prime. I'll tell you what K prime is in a second. You can also think of this as the intersection number between a Seifert surface for my Legendrian knot and this K prime. So what is K prime? Well, let's look at this picture down here for a moment. I want to think of, remember my knot is Legendrian, so its tangent bundle sits inside of the contact planes at every point. So this horizontal plane here is the contact plane, and then this horizontal plane here is the plane representing the normal bundle at this point, the normal bundle of K. So what is K prime? Well, if I take a push off, if I just choose any vector that's in this normal bundle and push off in that direction, so I get a point here, and that's a point on this knot K prime. So if I do that, let's draw the picture here. There's a push off, there's a push off, there's a push off, there's one there, and then K prime is this knot that I get by pushing off all along the knot that I started with. So this is K prime. This pink one is the Legendrian knot that I started with, and the Thurston-Bennequin number of K is the linking number with this push off, and in this example, you get a -1 there. Okay, so that's the Thurston-Bennequin number. It's just a linking number between K and this push off K prime. Okay. What about the next classical invariant? This one is called the rotation number. I like to think of this as sort of the number of rotations as we traverse K. So what does that mean? Well, if I think about my contact planes and I restrict them to a surface sigma that's embedded with boundary K. So let's say for now that this is a Seifert surface, I can choose a trivialization. So this is isomorphic to my surface cross R2. And then what I want to do is remember the tangent bundle of K sits inside of Xi. And in particular, if sigma is say a Seifert surface or any surface with boundary K, the tangent bundle of K sits inside of there, and this is a non-trivial vector field. Okay, so it gives rise to a map that I'll call U, from the circle S1 to R2 minus the origin. Okay, and the rotation number now with respect to this, this sigma, okay, is just the winding number of this map U. Okay, so let's think about it in this picture. Let's say I start here. So I start, this is my tangent vector. Okay, and I really just want to understand how many rotations do I do as I go around the knot. So I start here, that vector, as I move along the knot here, this vector starts to move in this direction. And when I get up to the top here, that vector looks like this. And then as I go down, I start to rotate back the other way until I get back to where I started over here. So I didn't do any rotation from here to here. And the same kind of thing happens as I go along the second half of this knot. I rotate from here to here and then back again. Okay, so as I traverse this entire knot, I actually don't do any rotation. So the rotation number of this knot that I've drawn is equal to 0. Okay, but in general, that could be a non-zero number. Okay, so we have these two quantities, the rotation, the Thurston-Bennequin number and the rotation number, and these are important for an inequality called the Bennequin inequality. So the most general version here is due to Eliashberg, so you should think of this as Eliashberg's Bennequin inequality. A lot of the time, any kind of equation of this form is referred to as a Bennequin inequality. So what is this? This is a theorem due to Eliashberg, and it kind of gets at this dichotomy that is present in contact topology between tight and over-twisted contact structures. So the theorem says that the tightness of a three-manifold is characterized by embedded surfaces in that three-manifold satisfying this kind of inequality. So the inequality says that for any embedded surface with Legendrian boundary, the Thurston-Bennequin number of the boundary plus the rotation number of the boundary is less than or equal to the negative Euler characteristic of the surface. So this is what it means to be tight. The kind of other thing you can be is over twisted, and you're over twisted if you contain an over twisted disk. So that's what I've drawn on this other side here, and I'll just show you quickly that if you have an over twisted disk, it's going to violate this Bennequin inequality. So the over twisted disk here has, so what is this picture? Well, this is a picture of the characteristic foliation, which is just the foliation given by taking the contact planes at a point and intersecting with the tangent planes of the surface. So we get, this is this intersection between these planes looks like a line generically, and there's this one point in the center where those planes coincide and we get a singularity in the foliation. And if you calculate the Thurston-Bennequin number of this over twisted disk, you get 0. On the other hand, the negative Euler characteristic of a disk is -1, and so this violates the Bennequin inequality star. Okay, so this Eliashberg Bennequin inequality is really at the heart of this tight and over twisted dichotomy. Okay, and the proof, Eliashberg's proof uses singular foliations and kind of analyzing the kinds of singularities that appear in those foliations, and it's all kind of very hands-on. The theorem that I want to present today is kind of a four-dimensional analog of this one. So it will be sort of, in certain cases, we can relax this condition that the Bennequin inequality holds for all embedded surfaces in Y, and instead of just requiring our surface to be in Y, we can allow it to venture into Y cross I. So it's kind of a, we're allowing more surfaces, but it seems like tightness might really be characterized in this more general way. So that's a little bit vague. Let me say more specifically what I mean. So here's a theorem. It says that if the Heegaard Floer contact invariant is non-trivial, then we have a Thurston-Bennequin inequality. So this is the same equation that I had on the previous slide, except now we're allowing surfaces in Y cross I, Y cross 0, 1, not just in Y, and they should still have Legendrian boundary in one of the endpoints. So here's kind of a schematic picture. Here's Y cross 0, 1. Here's my surface sigma. Over here, I have boundary sigma, and this is Y cross 1. So previously we had only sort of Eliashberg's inequality is really about surfaces embedded in Y with Legendrian boundary, and now we're saying, well, even if we allow surfaces in Y cross I, we still can't violate this inequality. So this is only in the case where the contact invariant is non-vanishing. So one thing I should say before I move on is that the contact invariant being non-trivial implies that Y is tight. So you can think of this theorem as saying, really, for certain tight 3 manifolds, we have a Bennequin inequality for embedded surfaces in Y cross 0, 1, and not just embedded surfaces in Y. And this kind of raises the question, well, does tightness always imply that we have this kind of Bennequin inequality for surfaces in Y cross 0, 1? And that's exactly the conjecture that Matt and I have. So again, this is Y. Here's my schematic picture, Y cross 0, 1. This is sigma. The conjecture says that YC is tight if and only if we have this Bennequin inequality for all embedded surfaces in Y cross 0, 1 with Legendrian boundary. So it's important to point out here that our proof relies on Heegaard Floer theory, and therefore on, as you saw in the previous slide, on the contact invariant being non-trivial. We know that there are tight contact structures with trivial contact invariant. So because of that, I think that Heegaard Floer techniques probably can't prove the conjecture. And my guess is that maybe there's some kind of way that's more spiritually similar to Eliashberg's proof, but I don't, at this point, all I really want to say is that Heegaard Floer techniques probably can't prove this because of the fact that the contact invariant doesn't completely categorize tightness. Okay, so this is the conjecture. The rest of the talk, I will tell you a little bit more about the theorem and how we prove the theorem. And you'll see as we go that the contact invariant being non-trivial is really important for the proof to work. Okay, so let's continue on. Right. So I do have to tell you a little bit about Heegaard Floer theory to prove the theorem and finish the rest of the talk. So I want to start by just giving you the definition of an invariant called tau sub xi of yk. So what is this invariant? Well, first of all, let's just say a little bit about Heegaard Floer theory. So HF hat of a 3 manifold is an F2 vector space, and it's the homology of a chain complex CF hat, which is filtered by, so if I have a knot in my 3 manifold, the knot filters the chain complex. So the filtration maybe looks something like this. I start with 0. It's an increasing filtration. So I'll label these F, M, Y, K, and F, M plus 1, Y, K. And it goes all the way up until I get the whole complex. Okay, so that's the filtration. And what is this tau invariant? Well, we sort of want, what we'd like to define it as is just sort of the filtration level at which the contact invariant shows up. But there's a caveat here that kind of complicates things, which is that the contact invariant doesn't live in HF hat of y, it lives in HF hat of minus y. So there's kind of two different things that I could do. So let's do maybe the easiest one first. So I could say, let's write tau of the contact invariant. This is going to be for k in minus y now. This is equal to the minimum m such that C of C is in the image of the map on homology induced by sort of including the mth filtration of k and minus y into HF hat of y. Sorry, minus y. That's hard to read. Let me move this over a little bit. So HF hat of minus y. Okay, so just to say one more time, this is the map. Let me do it in pink. This is the map induced by inclusion. So if I have k in minus y, and I look at the filtration induced by k on HF hat of minus y, I'm basically picking out the first filtration level for which I see this contact invariant showing up in that map. Okay, so that's a perfectly fine thing to define. There's another way that I could have kind of defined an invariant, a sort of tau invariant associated to a contact structure. So let me write down what that is. So tau sub c of yk is the minimum m such that there exists a beta in the homology of fm yk. So here I'm looking at the filtration induced by k in y, not in minus y. So the minimum for which there exists a beta such that if I look at the pairing between the contact invariant and beta, I get something non-trivial. So what is this pairing? This is the pairing between HF hat of minus y and HF hat of y. It's really, you should think of this as the pairing between homology and cohomology. So what am I doing here? I'm sort of looking at this filtration of k and y and picking out the first time I get something beta that pairs non-trivially with this contact invariant. Okay, and a fact, this is proved by Matt, is that tau c of yk, it turns out, is equal to minus tau of c of c, so tau, the contact invariant of yk. Okay, so there's a relationship between these two definitions, and I'll use them both in the proof, so that's why I kind of spent some time talking about this. Okay, so this is kind of the main tool for the main tool that we need to prove the theorem. So let's see how that goes. So I wrote the theorem again over here so you could be reminded. We just want to show that if the contact invariant is non-trivial, then I get this Bennequin inequality for all embedded surfaces in y cross 0, 1. So I'll just talk about the proof in the case where the boundary of the embedded surface is connected. It remains true if we have a non-connected boundary, but I think I'll keep it kind of simple for this talk since I don't have much time. So it's really just putting together two theorems. So the first one is a theorem due to Matt Hedden, it says that the Thurston-Bennequin number plus rotation number of the boundary of sigma is bounded by the tau invariant, tau sub xi minus 1, or twice tau sub xi minus 1. Okay. And now I want to combine this with another theorem that's due to Matt and myself. In this context, it says the following. If the contact invariant is non-trivial, then minus 2 times tau of the contact invariant of minus yk is less than or equal to twice the genus of sigma. Okay, so if you go back and watch my talk from this conference last year, I sketched the proof of, or I discussed the relative adjunction inequality. I will briefly kind of go over here why it implies this statement that I've written down here. Okay, so if you want to know more about that theorem, you should go watch my talk from last year, and I'll try to link it in the YouTube video, to this YouTube video. Okay, so why does contact invariant non-trivial imply this bound? Oops, let me use my highlighter. Imply this. Well, let's start with y cross 0, 1. Sigma is some embedded surface in there. And what I want to do is flip this around. So I'm going to look at really minus y cross 0, 1. So I just flipped it over. Here's minus y. So I can think of it as a cobordism really from minus y to itself. And that induces a map on Floer homology. So we know that HF hat of minus y maps by this. So this is really the map on Floer homology induced by this 4 manifold is the identity on minus y. And so in particular, if I look at the contact invariant sitting in here, it's non-trivial and it gets sent to itself, which is still non-trivial. Okay, so that's the condition that I need for the relative adjunction inequality to hold. And now what do I want to do? Well, let's actually tube this surface to the other side. And on this side we have an unknot. So I want to think of the surface as being a cobordism from the boundary sigma that I started with to the unknot. So now I have a cobordism from boundary sigma to the unknot, and I know that the contact invariant maps non-trivially to itself. So the relative adjunction inequality tells me the following. It says twice tau c of the unknot minus twice tau of the contact invariant of minus y. K, oops, here by K, I really mean, let's be careful, K is boundary sigma. So that's really what I should have written here. This is boundary sigma. Is less than or equal to twice the genus of sigma. Okay, and now this is equal to 0, and so I get this inequality that I claimed. Okay, so now let's finish off the proof. It's really just stringing these two inequalities together now. So I have TB xi of boundary sigma plus the rotation number of boundary sigma. That's less than or equal to twice tau xi of y boundary sigma minus 1. Remember, I told you that this tau invariant is equal to minus the tau invariant associated to the contact invariant of minus y of the same knot. So I have this, and by this inequality, we get that this is less than or equal to minus chi of sigma plus 1 minus 1. And so go away. And we get the implication that we wanted. Okay. So that's my talk. Thank you.